very much for the invitation to this really nice conference. And I'm going to have to give the standard apology. This talk doesn't really fit into the topic of this session. It does, but it does somehow fit between yesterday and today. And also in traditional fashion, it doesn't really fit the topic of the workshop either, because there's no infinite dimensions in this, but at least I'm going to take n. I care about larger values of n, so maybe that's close enough to finite to infinite, I guess. So with those standard apologies, we get started. So there will be, you'll have to bear with me for a bit, but I promise you that some CP maps are going to appear, but I'm going to start by motivation. And in the beginning, it might sound like this has nothing to do with quantum channels, CP maps, Markov processes, but we'll get there. So let's start by thinking about
CQE.
I couldn't fit it. Dissipative quantum Eigensolver. This is the title of the paper. For this audience, you can just ignore that part. It's just marketing. So the story kind of starts with the problem that I'm sure many of you are familiar with, where we have the ground state problem, one of the most important, in some sense, problems in physics. So we have some Hamiltonian, say, made up of local terms. So this is some emission operator in the simplicity. I'm going, because then I can use the word Cubitt, and I like the word Cubitt. I'm just going to have this to be a emission operator on n qubits, but this doesn't need to be 2. This could be a multi-partite system. We have these act non-trivially on some subset. Let's say these operators H sub I act as identity on everything except at most, let's say, k qubits, the usual local Hamiltonian. And then our input is some description. And then what we would like is to output some state, say mixed state, such that this state is in the ground state subspace. Phi0 is the vector onto the ground state, when that's the minimum eigenvalue. So this is the ground state problem, the quantum ground state problem, where we want to find or construct the ground state quantum mechanically, maybe on a quantum computer. And this problem is extremely important. It's important in physics. It's like a lot of dense matter physics, many body theory revolves around trying to understand these things. And also in industry, huge amount of computing power is deployed to try and solve this problem. But of course, there's an obstacle here, which is that we know that this problem is hard. So we know that this problem here is the ground state problem. Finding ground states is QMA hard. In other words, this problem is at least as hard as any problem in QMA. And QMA, quantum version generalization of MP, these are the problems that we expect that we can't solve. Even with a quantum computer, we can't solve this. Provably, modulo complexity theory conjectures. So we expect, this means that we expect, we're going to solve this problem. We expect to need exponential time in n. Size of the system, which so that seems pretty like bad news. And it gets worse because many physicists like to put assumptions on this Hamiltonian or physically motivated assumptions on properties that this might have that you would hope might make this problem easier. But there are no obvious physical assumptions we can put on H. Conditions that make this tractable. And the simple, sort of extreme version of this is even if we take the H to be classical, i.e. diagonal, all of the HI in the same diagonal, the same basis. And we assume it's got a spectral gap, constant spectral gap, say, so constant gap, i.e. The second smallest, the gap between the smallest and the second smallest eigenvalue of this is order 1. And let's assume it's even frustration free, which means, so in other words, that we have a ground state. Ground state is simultaneously the ground state of each local term. All of this, we can put all of these assumptions, and it's still at least NP hard.
Plus translation invariance also.
Yes, good, as long as we have 2D. Yeah, I could keep on adding plus a density of states assumption. It doesn't help. It's still NP hard, and we still don't expect to be able to solve this efficiently, even on a quantum computer, because we don't expect to solve NP hard problems in general on a quantum computer. And you make this a little bit quantum, it goes up to a sort of hard for a quantum class.
The left side of the board are the boundary conditions.
Well, I mean, this is not necessarily on some lattice or anything. It's just a local Hamiltonian. So the boundary conditions are absorbed in here.
If you ask for all the spectral gaps be gapped, uniformly gapped, are you better off? So you don't know what's known to.
No, I mean, everything stays at least NP hard for all of these assumptions. So all these conditions. Okay, nonetheless, this problem is so important that there are. Oh, and I should say that, so in this case, note that we expect, even in this case where I assume everything is a classical Hamiltonian, gapped, frustration free, it's still NP hard, so we still don't expect to do better than an exponential time algorithm. And there's a trivial exponential time algorithm here. We just brute force search. In the end, this is just a problem on bit strings, say, since they're restricted to qubits. So I could just brute force search over all exponentially many of them, see which one is the one that gives me the minimum value of the expectation value against this. So this is a trip.
Sorry to interrupt one more time. What about errors? If you want to do it up to 1 minus epsilon?
Ask me at the end of the talk, Marius, because I can tell you very interesting things about errors in the classical case, but I've only got 40 minutes. But yeah, it's hard even for classically, it's known by something called the PCP theorem, that it's hard even up to approximation. There's a whole story from the 90s of theoretical computer science about this. Yeah, so there's a trivial, I don't know what to write this, I'll just say it, but there's a trivial exponential time algorithm, just brute force search over everything. Okay, in the quantum case, this nonetheless, this is an important problem, which we know, and we don't give up on solving a problem just because we know in the worst case it's going to be hard to solve even on a quantum computer. We still need to solve this problem. People in industry doing materials modeling or computational chemistry still have to solve this problem. And they have a lot of computing budgets to do that. So there's a lot of algorithms have been proposed, particular quantum algorithms these days, that have been proposed to try and solve this problem, which we know are going to be exponential runtime, but that's fine. We have to swallow that in general, but nonetheless, they might be useful. So quantumly things get non-trivial quite quickly. So there's an obvious brute force, naive brute force exponential time algorithm for the classical case. For the quantum case, the brute force search algorithm, the analog or generalization of classical brute force search is not so obvious. And if anyone can tell me what it is. So this is just like, pick a random state, compute its energy. Quantumly, that's the phase estimation algorithm. So that already needs quite a lot non-trivial. The phase estimation algorithm is the quantum generalization of just the classical pick strings at random and check their value of this functional. Quantum mechanically, because it might not have we don't know what basis to look in, we have to use something already relatively non-trivial. And there are a lot of bunch of other algorithms. There's adiabatic state preparation. There's things called quantum imaginary time evolution. There's the famous BQE algorithm, variational quantum Eigensolver. All of these have some limitations. So we know they're going to be exponential time worst case. That's fine. We have to swallow that. We're not in the business of trying to find efficient algorithms in general. But these need these are non-trivial quantum. You need a sort of general purpose quantum computer just to actually run any of these, and we don't have one of those at the moment, despite what you might have heard from reading the media. The quantum computer has taken over the computing is now big business. It's not. We don't have a quantum computer can get anywhere close to running these algorithms. And this one is heuristic, so there's no guarantee it works. And there's another algorithm to add to this list, which goes back quite some way, over 10 years, which is called dissipative state engineering. And this is a result by, one of the results in a paper by Fistrata, Wolf, Sirac from 08, if you take the archive date. And this algorithm is what I want to talk about a bit more in a bit more detail. So this dissipative state engineering algorithm, this is the Fistrata, Wolf, Sirac 08 result. The paper has a number of different results in. I'm only going to talk about one of these, and the other two are also very interesting, but not relevant. So relevant here. They start with saying, let's assume that the Hamiltonian is frustration-free. This frustration-free definition is valid quantumly as well. And then if we have that, then without loss of generality, we can take H to be a sum over projectors. And so then they construct the following CPT map. We take this. Okay, I'm going to take my total Hill space dimension to be capital B. So what does this map correspond to? This just corresponds to measure each local projector or its orthogonal complement. And on, if you get wrong outcome, if you get the by perp outcome, just replace everything with the maximally mixed state. And this, and you can do smarter things than this here, but for simplicity in this talk, I'm just going to throw away everything and replace with the maximally mixed state across everything. So this is a very simple process. You can implement it relatively easily. You just have to do local measurements. Conditional on the outcome, you either carry on or you just dump everything and replace, start again with maximally mixed state.
So the PI are not orthogonal, right? So then
PIs, that's right. And these are local, K-local. So they're projectors that act as identity on all but K.
so the 1 over M is nothing like a normalization, or what is it?
Just that they're it's just this corresponds to pick one at random and
Well, I think you want the Hamiltonian to pi perp, the sum of pi
Thank you.
perp.
good. And it's not difficult to show that if you look at the fixed point of this process, that this fixed point that is the ground state or is in the ground state subspace. This is a relatively straightforward two-line proof. I leave it as an exercise. So what was very exciting about this back in 2008 when this paper came out, I think it was in Nature, published in Nature Physics, is the fact that this algorithm has some very nice features. Apart from the fact that it's a relatively simple local process, it's also completely irrelevant what state you start from. You might not be able to initialize your qubits, doesn't matter. You're inexorably driven towards the state you wanted, the ground state, this many body Hamiltonian. And if a cosmic ray comes in and completely scrambles the data halfway through the computation, it doesn't matter, just keep running it, it will get driven back to the right thing. So there was an argument that this was somehow inherently resilient to noise, and very simple to implement, more relatively simple to implement in the real world. And that's very nice. And just to flag the mixing time of this, so the time to converge epsilon close to the fixed point. Well, this is going to be something at least going as 2 to the n, but one could show that, but that's what we expect. The complexity theory obstacles mean that we don't expect to do better than that, so that's not a big disadvantage. But it only works for frustration-free Hamiltonians. And there's a lot of papers in the subsequent literature building on this one, which start off by saying, unfortunately, this only works for frustration-free Hamiltonians, so we're going to do something different. And then you develop these algorithms or various other.
Good question. I think you also need to know what the eigenstates are, right? Structure.
It's fine for frustration free because without loss of generality, you know that the eigenvalue, so the ground state, the minimum eigenvalue is 0 without loss of generality, and then you have a gap of, or you don't need the gap actually, you just need the and so that's okay. You can just rescale and shift together. So I'm trying to, you're now trying to find with this formulation, you're trying to find the state of the kernel of this thing. Okay, so what I'm gonna try and do in this talk is to explain a process that achieves everything you would like about constructing a quantum Markov process that lifts this, that actually in general works for any, will converge to the ground state of the Hamiltonian without any assumptions on the Hamiltonian, without any knowledge about its properties, just its description. So this is what I call the dissipative quantum eigensolver. So it's a simple local procedure, which I will define in more detail in a moment, what that actually means, and it's guaranteed to find the ground state and no conditions or assumptions or knowledge of, no assumptions on the Hamiltonian, or you don't need to know anything about the Hamiltonian other than its description. And so there are two kind of things that allow us to overcome this obstacle that this only works for frustration-free Hamiltonians. And so two key ideas are replace the projective measurements by weak measurements. And make use of the measurement information. So in this process, if you think about what this means operationally, you perform a projective measurement, do something conditional on the outcome, and then you completely forget what outcomes you got. Instead, we make use of the information we're gathering along this process, and we can do a bit better. So that's where I'm going. So an outline.
Can I stop you here before you go into this? So when you say the mixing time is at least 2 times, this is universal. It doesn't depend on the Hamiltonian. It's always, as I understand.
No, sorry, that's worst case.
Okay, that's reassuring. So there are it does depend a bit on the Hamiltonian. There are some cases when you can be more.
Yes, and indeed in their paper they have cases where it's poly. Yeah, sorry, thanks.
Question related to that. So for an Ising Hamiltonian, say chain where it is easy, is that reflected in there? So and then also say polynomial.
I said I've taken a rather simple case here where I do something pretty dumb. If I do something smarter here, then yeah, for that case, I think you can probably make it. How about, you mean quantumizing the transverse field?
No, just the Ising like.
Translation variant 1D Ising.
Yeah.
Then I think, yes, you can make it efficient. But if you go to 2D and have local fields, it's already NP hard and then.
So it is reflected. So the NP hard, the classical NP hard is somewhat reflected in the quantum worth.
Definitely, yes. The hardness has to be. So you've got a family of Hamiltonians that's hard, that's NP hard. Definitely, you're going to get exponential mixing time or a whole bunch of complexity.
For the ones where you know it's easy.
It's a good question. I think you could probably always make it poly time for ones that are known to be easy, but not necessarily with this. But doing something smarter here that's actually using some knowledge of the structure of the.
And I guess you will comment on your approach regarding the mixing time and the gap.
The mixing time will be exponential. The runtime, because this is a general algorithm that will work for any Hamiltonian. So in the worst case, it better be exponential time or complexity theory collapses. And
it should depend. So that
it'll always depend on the Hamiltonian. So all of the point of all of these algorithms, why do people come up with algorithms for, despite the fact they know it's going to be exponential time? Because they hope that that's the worst case. They hope that on interesting systems that you care about, you won't hit the worst case. And that's how things work classically as well. Lots of algorithms for solving NP hard problems. You just like sat solvers are amazing, and they typically don't hit in practice the worst case, and you actually get efficient. But these are not provably going to work, and they're heuristic and etc.
Very stupid question. So the easing model is frustration.
No, but there's more as so I was hesitating about the Ising model. I'm pretty sure you can probably use the structure of the Ising model because it's even for the quantum case in 1D, because you can map to free fermions, then I think you can.
It isn't frustration because you've mentioned frustration.
Yeah, their algorithm, I'm mentoring 1 out of 3 results in this paper. This is the one that's for, you have a description of the Hamiltonian, it goes to the ground state. If you know a bit more about the structure of the ground state, you can do something, and they did do something different. So for example, if the ground state is an MPS or PEPS, the matrix product state, and you have its description, you can make this polytime, for example, they prove that. You can also do polytime universal quantum computation with this process, but that's a different problem where you know something about, or you know the ground state already, or you know at least something about the ground state. Of course, finding what the ground state is in general is hard already. Yeah, but there's a lot more in this paper that I'm touching. Okay. So what I need to kind of go through, and we'll see how far we get, is so I need to divert very briefly into the theory or some results about approximate ground state projectors. And then bonus material if we get there, which no doubt we won't. So this is roughly an outline of where I'm going. So I need to divert and then just introduce the definition of AGSPs and the results. And then first thing I'm going to do is construct an algorithm or a process like this, where the fixed point actually gives you the ground state for an arbitrary Hamiltonian, but it's going to have some deficiencies. You'll still need to know some knowledge of H. This kind of uses the first ingredient. Then I'll go to this second one, which improves this by getting rid of the requirement for any knowledge about the properties of H, and that uses this second ingredient. So that's roughly where we're going. Okay, so I first need the definition of an approximate ground state projector. So approximate ground state projector is a Hermitian operator, which satisfies 3 properties. The commute with some projector pi. It's acting on the projector, it's lower bounded, the operator sense by some parameter real number gamma. And for the orthogonal complement, sorry, I have that around. And finally, it's close. This projector pi is close to, this is the ground state projector that we're interested in. Okay, so this definition is not due to me, or rather this is a generalization of a definition from a paper by Itai Arad et al. From 2013. This is a generalization of their definition. Their definition has gamma equal to 1, epsilon equal to 0, but then they have an extra condition about the blow up of the Schmidt rank, which we don't need. So everything that they did, all of the AGSPs they constructed are satisfy this definition, but it's a bit more. So why is this an approximate ground state projector? Well, because this acts something like a projection, except it's on a projector that, you know, if this was 1, then this would really be leaving the ground state subspace invariant, and it would be shrinking the norm on the orthogonal complement of that, but it's not quite the right projector, it's only approximately right, and it doesn't, the orthogonal complement isn't in the kernel, it just shrinks it, and it doesn't perhaps fully leave the subspace invariant, it shrinks it a little bit, but not too much. So that's kind of the intuition behind this. Okay, what
Arad et al. Proved, amongst many other things, is that they constructed families of good approximate ground state projectors. So if we take, I'm only going to sketch this. So if I take a suitably rescaled Chebyshev polynomial, and suitably rescaled, I'm hiding quite a lot of, sorry, suitably rescaled. Then they showed that CL of H, if I apply that to the Hamiltonian to an operator, the obvious kind of extension from the reals to just apply this to the eigenvalues of this, use the spectral decomposition. Then this is a delta 1, 0 approximate ground state projector. So say that I should have written this. K is a gamma, delta gamma epsilon AGSP. So that this is an AGSP with parameter delta. Square root of delta is 2e to the minus L. L is the degree of the order of the Chebyshev polynomial. And this has some stuff in it. Anyway, this is exponentially small in L, the degree of the Chebyshev polynomial, which is nice because we want delta to be small. We want to project away or decrease away the norm on the.
Sorry, the definition is a property of K's, so there should exist a pi such that.
Yeah, sorry. Is an approximate ground state projector for pi 0. Thank you. And furthermore, it's not difficult to show that if H is a local Hamiltonian, then this implies that CL of H is also a fairly local Hamiltonian. Where these there are M primed is poly, let's just write poly M. And for constant L, and whatever it's K is L times K, I think. Okay, so
It's a simple question. You're taking a delta 1, 0, but as soon as you put the last thing as 0, where is it approximate? Because I thought epsilon was playing the role of approximation.
well, so no, also the delta and the gamma. So it would be an exact projector if gamma was 1, delta was 0, and epsilon was 0. They didn't, the original definition of AGSPs didn't have this. They had epsilon equals 0. I've generalized it a bit. And they also didn't have gamma. They had gamma always equal to 1. So they constructed what they would just call an AGSP. This has some extra properties as well that I don't need, which is the condition that I've got rid of my definition. Okay, that's useful. So there are good AGSPs that are still constructed out of sums of local emission operators. And perhaps this talk kind of important will be the following, but if I have a I take this operator, or this operator. And then I take the product in the other direction. This is also so what are these? A prime I is density minus HI. It's basically just related to the local terms in my Hamiltonian. Kappa I is just sort of basically the norm. Over these. There's a full definition. But anyway, this object is delta prime, gamma primed, epsilon primed AGSP with delta primed as something that's basically good. This is the second smallest eigenvalue. So basically this is a reasonably, this is an AGSP at least with some parameters that are related to the spectrum of well up to epsilon errors of epsilon order epsilon squared, and this epsilon primed is order epsilon squared. Okay, the main story here is that this is this is an approximate ground state projector. This is not very difficult to prove. Proof is like binomial expansion plus standard results about perturbation of spectra and spectral projectors. Why do I care about this? Because I care about being able to implement this. Actually implement this operator. Now, if I've just got a measuring the whole Hamiltonian, it just might be a sum of local terms, but that doesn't mean I can the global operation to measure it. I would have to do one of these algorithms, phase estimation or wide, to actually be able to measure the energy with respect to the global Hamiltonian. But this I can do on a quantum computer simply. Well, operationally, this means, what does it mean? It means I weak measure the local terms in the Hamiltonian one after another. So that's something where each operation in this and the product, I just need to measure a qubits, weak measure them. And then the next one, and then the next one. So this is like has the additional property. This is an AGSP, but it's locally implementable. Okay, that's all I need about approximate ground state projections. And now I can finally write down another CP map.
Sorry, what happens for epsilon equal to 0? So you should get an exact.
Epsilon equals 0 is pretty bad because you're doing nothing.
Yes,
It's a given entity.
Should you get an exact?
No.
0?
No. I mean, you get a yes, but you get a 1, 1, 0, which so you've got a approximate ground state projector that doesn't reduce the norm on the orthogonal complement at all. So it's, it's an AGSP, but with terrible, stupid parameters. So it's a trivial one. So it's trivial in AGSP, but
Even as it is pretty terrible. because
it's pretty terrible. Yeah.
Gamma and delta are pretty simple. Sorry, I'm just helping you to set up the punchline.
Thank you. Good. But remember, you have to get out of the mentality of wanting anything to scale polynomially here, because we know it's all going to be exponentially bad. The difficulty is succeeding at all, not doing something well. Okay. So now I can at least state how you can construct a process that does what for Strata-Wolf and Sirac didn't manage to do for frustration-free Hamiltonians more than 10 years ago. So we have let's assume we have an AGSP for ground state projector sub 0. And now this is on total Hilbert space dimension D. We're going to take the ground state degeneracy, I'll call it N. Notation. So if I take this map, dagger here, although it's Hermitian, so it doesn't matter. So this map just, what am I writing down here? It corresponds to measure the approximate ground state projector. And if we use this one, we know we can do this by just locally measuring each term in the Hamiltonian weakly. And then if you get the outcome K, then great, these are now generalized measurements. We get the outcome K, I just carry on. If I get at the outcome, the other element of the generalized measurement operators, so K forms a general set of generalized measurements with something that just by normalization has one identity. If we get the other outcome, so basically measure K, and it's the other operator that completes it into a full generalized measurement. If you get the wrong outcome, just replace with maximally mixed. So very like the Strata-Wolf Sirac map, but now we're weak measuring the terms in the Hamiltonian rather than collective measurements. Okay, so let's look at what the fixed point of this is. Look at the fixed point is, I claim, exactly equal to density minus K squared inverse over trace of this for normalization. And trace of this against the ground state is in lower bound it. So let me sketch the proof of this and then comment on it. Yes, I know, Andreas, this is terrible. Actually, it's not so terrible. We'll see. So this is very nice. You can get exact analytic solutions for this. And why? Because if I write down the fixed point equation, the state that's left invariant by this, put it back here if you want. This equation looks like this, where C is just brevity is trace of rho infinity, trace K, rho infinity K. D. This equation is a discrete Lyapunov equation. And it's a well-known or a rather simple exercise to see that this has a unique solution. Unique, in case as long as gamma is strictly less than 1 solution. And that unique solution is just given by what I claimed. This is standard theory of Lyapunov equations. And then this bound follows by the bound on trace of follows by definition of an approximate ground state projector. So use the properties of what I put here and use those in this equation. Gives you this bound. Okay, so we have a process whose fixed point is got overlap with the ground state projector that's lower bounded by this. So if I use this, well, if I put together this, the AGSP family constructed via Chebyshev polynomials by Arad et al. And I approximate that guy in this kind of way. So remember, this gives me this is itself a local Hamiltonian. So when I put it through this Chebyshev polynomial, so I can apply this lemma to that one, I actually get something that is good here. I get this close to 1. So corollary. I use CLH plus the lemma, the local AGSP lemma, and choose epsilon equal to n over d. I get that I just algebra get that this is equal to 1 minus epsilon over something that goes as order e to the minus L. Okay, so this, as I make my, this is going exponentially to 1. Okay. So as I make the degree, I can choose the parameters of this Chebyshev polynomial such that I can make this close to 1, and epsilon I can choose smaller than this. So I'm just sketching this result because it's got a big limitation. And the big limitation is the fact that I hid a whole bunch of I hid some sins in this suitable rescaled Chebyshev polynomial. So problem is that to suitably rescale the Chebyshev polynomial, I need to know the spectrum of the Hamiltonian. Finding the spectrum Hamiltonian is itself QMA hard. So this shows that there exists a process whose fixed point is close to the ground state of any Hamiltonian, but we can't construct it efficiently. We can't know how to construct it efficiently. And there's no way to actually write it down other than doing an exponential time computation. Okay, so that was this. How do we get around this? Well, I said that the way to get around this is to make use of the fact that if we were to implement this map, we would do it by measuring this operator. And condition on the outcome, we would do something. But that means every time we apply one iteration of this map, we get a 0, 1 outcome that we can make use of that information. So under the same notation as before, I'm just going to instead split this into a quantum instrument given by two completely positive but no longer trace preserving maps. The first of which is just the first part of what I wrote before, and the other is the other part of it. So this is just these two parts. This measurement outcome and this measurement outcome followed by resampling or replacing with maximally mixed. And now if I iterate this quantum instrument and I stop on n again. Let's see, I get T0 outcomes. Then one can show that the despite and now you okay. For 0. This is much nicer. So if I do this, then at this stopping time, so the density matrix at the stopping time, so the time at which I got, let's get Z0 outcomes, now has overlap with the ground state that is close to 1, and it goes exponentially to 1 as I make the number of zeros I wait for go to infinity. And now this I don't need to use the non-constructible ADSP. I can just use the basic one where I shove the Hamiltonian itself that I've already given through this to generate a local approximation to it. But this is not particularly difficult actually to prove this, but I think I'm out. I will skip the proof of this. Tell you a bit more about at least one more result about this. So we know that this must be exponential time in general, but in fact we can actually compute exactly the expected stopping time of this. It turns out to be exactly this quantity. And the proof of this, how long have I got? How long have I got?
1 minute.
1 minute. Okay. Let me give you this proof because it's kind of cute. Or I'm only going to sketch it. Let this be the teeth measurement outcome. Now I'm going to define, this is just a 0, 1 valued random variable. I'm going to construct a new random variable, sequence of random variables. Doesn't really matter too much what this looks like. And this is for the 0 and the 1. And this is just defined recursively. The point of this is that this, if I compute the expectation value of this random variable, it's equal to m. In other words, this defines a martingale process. And that also means that it's a martingale. So if we take the value of this random variable at the stopping time, by Dub's optimal stopping theorem, that's also a martingale. And actually, this property is allows us to get out the expected stopping time in a cute way. Now, okay, at time t sub z, we just had z zeros. So we know then that the stopping time, Z steps before that, value of this the variable must have been that just by construction. And we know that it satisfies this recurrence. We go back k steps, it's 1 over some probability. So this just follows just from the definition of this. And there's a nice intuition about what we're doing here. What have we done? We've simply, what is this M? This is just the process of betting on the outcomes of the sequential outcomes. And it's defining betting so that the odds of winning are the odds are fair, so that the payoff is a fair betting game. This means that that's why it's a martingale, so we expect on average to not win anything. And this means that now if we take expectation values of both sides of this equation, we know that this here, this is equal to the expectation of M0, the martingale property. And we know that that's equal to 0. And now this, we should take expectations here. And then this cancels with that, and we have that the expected stopping time is, and we end up with the expected stopping time that I claimed here if you do the algebra. Okay, I am completely out of time. So this gives so just to summarize the rest of the story. So this is a very, we can construct these really nice quantum Markov processes that actually do something useful, they're locally implementable. And with a bit of more effort, there's still some dependence in constructing this on the spectrum, needing to know something about the spectrum of the Hamiltonian. It's buried in the gamma and delta parameters. But by choosing a suitable decreasing sequence of epsilon, you can get rid of this requirement as well, and actually achieve what you would like for this, where you have a process that you can just construct from the description of the Hamiltonian. It's provably guaranteed to converge to the ground state subspace without any assumptions at all and knowledge of the Hamiltonian. And the final thing that I should highlight, and go read the paper if you want to know about it, is that one can make rigorous these claims about that this process is robust to errors. So one can prove, you know, the paper, it's a bit of some nice theory about sort of the non-commutative generalizations of probability of stochastic process theory. One can prove that if you've got a constant rate of error, of noise in this process, so you don't have this process, you have something delta close to it, the final outcome will be delta close to the correct thing. So this means without any extra qubits, no error correcting codes or anything, you don't have full fault tolerance, but you have something that's kind of fault resilient. Even though this process will run exponentially long, the errors don't accumulate. And one can actually make that rigorous. There's a lot more that I'm not going to have time to talk about, so ask me in the questions if you want to hear the rest of the talk. Thanks a lot.